Today we're going to look at inference for linear regression. Regression applies to situations where you have two quantitative variables and you want to explain or predict the behavior of one variable, called the response variable, using the behavior of the other variable, the explanatory variable, in some sort of a linear relationship. Now, all linear relationships have a slope and a y-intercept, and the basic job in regression analysis is to figure out what would be a suitable value for those two things, the y-intercept and the slope. The first thing you do when you're doing this kind of analysis is plot your data. We put the response variable on the vertical axis and the explanatory variable on the horizontal axis. And then we plot the joint occurrences of each of those variables for each individual in the data set. So for one individual, we have an x value and a y value. We plot that point, and so on for all the other values in the data that we have. And then we try to fit a line to those data as best we can. And when we do that, we will get something like this, a line which will have a y-intercept of a and a slope of b, and an equation y hat, that is predicted y, equals a plus bx. Now, the line's not going to fit the data perfectly. Usually you have some overestimates and some underestimates in the data, because generally the scatter plot's not going to be a bunch of perfectly collinear points. And because of that, because there's a difference between the y values that you observe and the y values that you predict on the line, those differences are called the residuals. They are the difference between the observed y and the predicted y on the line. And the way we fit the line best is to choose values of a and b that minimize the sum of the squared residuals. So that's what we call the least squares criterion. The best fit line, or least squares regression line, is a line that minimizes the sum of the squared residuals. Now for this line, the slope is b, and that can be calculated to be r, the correlation between x and y, times the standard deviation of y divided by the standard deviation of x. And the y-intercept is a. That's the mean of y minus b times the mean of x. Now, presumably underlying this relationship that we see is potentially a much larger population of potential values that we might get if we were to take measurements many, many times. And what we get is something like this. We were to take many observations where we look at x1 as being a fixed value, and then we take various observations. We might get some distribution of y values for that value of x. For x2, second value in our data set, we might also get a distribution of y values, and so on for x3 and x4. Somewhere in this scatter plot, we believe there is a true relationship, because the true relationship between not y specifically, but the mean of all the y values on each of these distributions and the x values in our data. And this true line, mu y equals alpha plus beta x, has a slope of alpha and a slope of beta rather, and a y-intercept of alpha. There's one other parameter that applies here for this line, and that's this third parameter, sigma, which is the standard deviation of these distributions of y values for each x value. So that's the spread about the line. And we estimate those three things, alpha, beta, and sigma, with a, b, and s. So we just introduced a new thing, s. We have to describe what that is. Alpha and a both apply to y-intercepts. Alpha is in the true model. A is in the estimated model from our data. The slope is beta in the true model, or b in the estimated model from our data. And the spread about the line is sigma in the true model, and s in our estimated model from the data. Now this s is very important for all the things that we do in regression inference. It's the standard error about the line. That's what it's called. And what it is, specifically, is the standard deviation of the residuals. Now the way we calculate that is we take the difference between each observed y value and its corresponding predicted value on the regression line. We square those differences. We add them up. We divide by n minus 2 and then take the square root. So this is basically how we calculate a standard deviation. In this situation, we divide by n minus 2 instead of n or n minus 1 because we've used up 2 degrees of freedom calculating a and b, and so we only have n minus 2 degrees of freedom left to calculate s. But the nice thing about these three things, a, b, and s, is that they are unbiased estimators of alpha, beta, and sigma. So they have that very nice quality, which is very useful. Now, when you're doing this kind of inference from specific data values, trying to figure out answer some questions about the true relationship, these are the conditions that should apply. First condition is that the true relationship is linear. The way you test that or check that is you look at your scatter plot. The scatter plot should be linear. If it's noticeably curved, you should straighten it before you go on and then see if you can do this process after that. We'll talk about how to straighten scatter plots in a few days. The residual plot also should not be curved. What you might see in your scatter plot might look fairly straight, but then when you look at the residual plot after you do the regression, you might find that there's some curvature to that, and a perfectly straight line relationship might not be appropriate, and you can fix that using techniques that you'll learn later. Second condition, the observations in your data should be independent. The residual plot should show no pattern, and we'll show an example in a few minutes in a future video about that. Third condition, the standard deviation sigma, or the spread about the line, should be constant for all values of x. Now the way you check that is look at the scatter and the residual plot. That should be uniform for all values of x. And then fourthly, the deviations in y about the true line are normally distributed. That means the residuals should be normally distributed, and you can look at the residuals and see if that's the case. An easy way to do that is to make a normal probability plot of the residuals, and that should be linear. So those are the conditions that apply to inference for regression, whether you're doing confidence intervals or tests of significance. These are the things that you're going to want to look at and make sure that they all apply.